So, welcome you all in my next lecture. So, in my last lecture I talked about, of course, I started with the notion of quadratic forms and classification of quadratic forms I have discussed, and you know that classification of quadratic forms, if I am starting with a symmetric matrix and then I am associating a quadratic form, and then the classifications I have done, I have discussed in terms of some properties of your quadratic form, and then I said that since a symmetric matrix is involved in quadratic form, so therefore it is expected that in terms of eigenvalues can I talk about that classifications. So, that is my plan, is to talk about those classifications of quadratic form or symmetric matrices in terms of eigenvalues, and then of course, I will talk about there are some conditions on those given a functions f. So, there will be Hessian, and then on that Hessian matrix I can give some conditions, and then I can talk about the points of extremum or existence of local extremum or relative extremum or global extremum or absolute extremum. So, that is my plan for today's lecture, and if time permits I will talk about Lagrange multipliers and exact differentials. So, now as I promised, I should classifying my quadratic forms in terms of the nature of the eigenvalues. I just said because a symmetric matrix is associated with that quadratic forms, that is the title I have written, classifying quadratic forms from the nature of eigenvalues. Okay. So, what is my quadratic form? That is I have written as a statement or as a theorem. What is that? So, if I have a quadratic form Qx which is xt hx starting with a symmetric matrix H n cross n, where xt is a point in Rn, then what about the classifications of those quadratic form in terms of eigenvalues? So, what I am saying, first one, if all the eigenvalues of H are positive, then the corresponding quadratic form or the symmetric matrix is positive definite. Positive means strictly positive I am talking about. If all the eigenvalues of H are negative, then the corresponding quadratic form or symmetric matrix is negative definite. If your matrix has both positive and negative eigenvalues, but does not have 0 as an eigenvalue. So, that means I have a matrix. So, it will have positive eigenvalue as well as the negative eigenvalue, but it does not have 0 as an eigenvalue. Then I will say that the corresponding quadratic form or symmetric matrix is indefinite. Okay. Now, if 0 is an eigenvalue of H, so it is called semi-definite, the corresponding quadratic form and symmetric matrix if 0 is an eigenvalue. In particular, in case of semi-definite, if it is a semi-definite form, that means if 0 is an eigenvalue. If all non-zero eigenvalues are positive, then I will say that this is positive semi-definite. If all non-zero eigenvalues are negative, then I will say that this is positive. Okay. So, this is positive, or I have written in one sentence, if all non-zero eigenvalues of H are positive or negative. If it is all positive, then I am saying it is positive semi-definite. If it is all negative, then I am saying that it is negative semi-definite. I think this should be not definite, it should be semi-definite. This is a typo, negative semi-definite. Okay. So, that means if I have a matrix, symmetric matrix, if all the eigenvalues are positive, strictly positive, then it is positive definite. If all the eigenvalues are negative, it is called negative definite. If one of the eigenvalue is positive, another eigenvalue is negative, and 0 is not an eigenvalue, then those symmetric matrix or the associated quadratic form I am talking about, it is indefinite. And if 0 is an eigenvalue, then I will say that it is semi-definite. In particular, if all the 0 is an eigenvalue, of course, if all other non-zero eigenvalues are positive, this is called positive semi-definite, and if all other non-zero eigenvalues of H are all negative, then I am saying that this is negative semi-definite. So, that is how the classifications of the quadratic form associated with the symmetric matrix in terms of the eigenvalues of H or eigenvalues of the symmetric matrix. I think let us see some example, then it will be more clear. Okay. So, this is example, like first example, it says that this matrix is a symmetric matrix first of all, and it is positive definite. Of course, it is a symmetric matrix because it is a diagonal matrix. Okay. So, therefore, it is symmetric, and look at the diagonal elements 1, 2, 3, and for diagonal elements, what are the eigenvalues? Just the elements of the diagonal. Now, what are the elements of the diagonal? 1, 2, 3. So, these are the eigenvalues and all are positive. So, therefore, it is positive definite. Negative definite, again I am talking about diagonal matrix, diagonal elements are the eigenvalues, it is symmetric, and all the eigenvalues are -1, -2, -3, these are all strictly negative. So, therefore, it is negative definite. Indefinite, again You have look at the diagonal elements, because I am dealing with diagonal matrix. Eigenvalues are 1, -2, -3. That means one of the eigenvalue positive, another eigenvalue is negative, and 0 is not an eigenvalue. So therefore it is an indefinite. Semi-definite, look at the diagonal elements, it is 1, 0, -1. So eigenvalue 0 is an eigenvalue. So therefore this is a semi-definite matrix. Positive semi-definite means, okay, look at the diagonal elements 1, 0, 2. These are the eigenvalues. 0 is an eigenvalue. Other non-zero eigenvalues are positive. So therefore this is positive semi-definite. These are positive. Similarly, negative semi-definite means 0 is an eigenvalue along with other two non-zero eigenvalues are negative. So therefore this is negative semi-definite. So this is positive semi-definite. This is negative semi-definite. These are the examples of positive definite, negative definite, indefinite, semi-definite, positive semi-definite, negative semi-definite matrices. Okay, in particular, if I have a true cos 2 matrix, real symmetric matrix, then you can also talk about positive definite, negative definite, indefinite and semi-definite in terms of the determinant of the matrix, because determinant you can easily calculate because it's a 2 by 2 matrix. Along with the elements involved in that matrix, sign of the elements of the matrix, sign of the elements involved in that matrix, along with the determinant, you can talk about positive definite, negative definite, indefinite and semi-definite. So that's, I wrote it as a theorem. So let's start with the H whose elements are A, B, B, C. Of course, it's a symmetric matrix. That means these two should be same, B, B. It's a 2 cross 2 symmetric matrix. Then I am saying that symmetric matrix H is number 1, positive definite. If the determinant of H you can easily calculate, which is AC minus B square, which is strictly positive, along with the fact that the element A, that means 1, 1 element A, it should be strictly positive, at the positive side. Negative definite means what? If the determinant AC minus B square is positive, however, the 1, 1 element A should be strictly less than 0. That's called negative definite. Indefinite means if determinant is negative, that means AC minus B square is less than 0, and semi-definite means if the determinant is 0. Therefore, if I have a 2 by 2 symmetric matrix, then I can talk about positive definite, negative definite, indefinite, semi-definite in terms of the determinant of the matrix along with the sign of the element 1, 1 element A. That will be useful later when I will talk about, I have a functions from same R2 to R, then the corresponding Hessian matrix, it will be a 2 cross 2 matrix. In fact, 2 cross 2 symmetric matrix if I assume some nice conditions on F. And then using that positive definite and negative definite, I can talk about the existence of local maxima and local minima. That is what it will be very useful. Okay, so just few examples, whatever I have discussed in my last theorem, the examples. So positive definite means what? Determinant should be positive and 1, 1 element should be positive. So if you just calculate, determinant is 7, which is positive, 1, 1 element A is 2, which is positive, that means it is a positive definite matrix. Negative definite means determinant is positive, 1, 1 element is strictly less than 0, so therefore it is negative definite. Indefinite means determinant is negative, and semi-definite means if you just calculate determinant, it is 0. So it is a very kind of very simple examples that it has these properties. Okay. So now as I said that the notion of quadratic form and the symmetric matrix came into the picture because I want to talk about some conditions on my functions so that I can say that okay, these are the points where my functions attains relative maxima, relative minima or absolute maxima, absolute minima, and there I said Hessian matrix plays a very crucial role. I think these slides already I have discussed when I talked about Hessian matrix. Just to recall those Hessian matrix, I put it again here. So I am just going very first that let S be an open set in Rn. Suppose you have a scalar field and suppose your function is twice differentiable, nice, at the point x naught, then the corresponding Hessian matrix which is whose ijth element is dijf at x naught, or sometimes I will say that this is nothing but the Jacobian of your gradient matrix F at the point x naught, or I should say at x naught. So that means Jacobian of your gradient vector, because if F is a map from S subset of Rn to R, then your gradient of F is a map from Rn to Rn, and then Jacobian of the map gradient of F at the point x naught, which is nothing but the Hessian. Okay, and so therefore you can easily write. So its first row is nothing but the, you talk about the first order partial derivatives and then perform the again one more derivative or del f del x1, that means this is 1 1 1 2 up to 1n and this is actually n1 n2 up to nn. So that means this is perfectly all right, you can easily write it your Hessian matrix. Okay. Then the second derivative of f x naught denoted by f double prime at x naught, it is a map from Rn to R, and there is a relations with the Hessian matrix and your total derivative. So, total derivative is a linear transformation, it acting on x is nothing but x t h x. Now, you can I think connect what I am trying to say. So, earlier what? If I have a symmetric matrix, I am starting with a map Q acting on x which is nothing but x t h x, and that I say that it is a quadratic form. Now, we look, if your function is twice differentiable, then the derivative map at the point x naught, it is nothing but a quadratic form, and where matrix H is a Hessian matrix. Now, if I assume that my second order partial derivative are exist and continuous, then your Hessian matrix is a symmetric matrix, then you will have the associated quadratic form, and which is nothing but the total derivative acting on x. So, that is how it connects. That means, if I want to talk about on the map or the second derivative, that means automatically Hessian came into the picture, right. So, this I already explained, right. If the second order partial derivative of f are continuous, then mixed partial derivative exists and they are equal, and therefore, the corresponding Hessian is a symmetric matrix. And this action is very important. With this action, I will talk about. So, that means, once I have the actions of the total derivative or double derivative of f at x naught, and there is a relations with the Hessian matrix. Now, I can have a classifications of matrix or the associated quadratic form. Then, using that one, I will conclude that given a functions, when it attains your relative maxima and relative minima, that the second order derivative conditions you will see that will come when, of course, in very special case I will talk about, like if I have a functions from R2 to R, so that your Hessian is a 2 cross 2 matrix, and I already discussed the definiteness conditions for a 2 cross 2 matrix. With that assumption, you will see what are the kind of conditions will be there, so that I can talk about when my functions have a relative or maxima or minima or relative extremum. Okay, that is why I am just written as a second derivative test. Okay. So, that is the second derivative, because second derivative, if my function is twice differentiable, then second derivative and the Hessian has a connection. Okay, so that is why. So, this is the motivation and idea. If I have a map from R2 to R, then I already discussed extended mean value theorem or Taylor's theorem up to second derivative term. What is that? That means f of x naught plus x minus f of x naught, that can be written into first order partial derivatives and second order partial derivative, because I am talking about extended mean value theorem or Taylor's theorem up to second derivative term. Okay. So, therefore, what is that? This is the corresponding first order or partial derivative term, that means x times f x at x naught plus y times f y at x naught, and then you will have a second order partial derivatives term, that means x square f x x 2 x y f x y plus y square f y y. Of course, you can easily understand that I am talking about f of x y at p is same as f of y x at p. That means, I am assuming that second order partial derivative exists and they are continuous. So, therefore, their mixed derivatives value will be equal. That is why 2 x y, I will just club it together. Okay. So, therefore, now here I have written that the magneta color, that means this color, now this is x square f x x at p plus 2 times x y f x y at p plus y square f y y at p. Now, this term you can write in terms of the quadratic form. Okay, what is that? This is q of x, which is nothing but x transpose h x, and that is exactly equal to your double derivative at the point p acting on x. Just now I have discussed in my last slides. Okay. So, therefore, this portion is nothing but the quadratic form, and therefore, the motivation is nature of Hessian matrix implies the nature of critical point. Yes, you see, now this is the connections. So, that is why I had to introduce the quadratic form, symmetric matrix, classification of quadratic forms. So, the nature of the Hessian matrix, and nature means what? I already discussed various classification like positive definite, negative definite, positive semi-definite, negative semi-definite, indefinite. Depending on that, I will talk about the nature of my critical point. That means, at some critical point, if something happens, some kind of definiteness, if I tell you, then with that condition, I will say that, okay, at that point, either it is a relative maxima or relative minima, or it is a saddle point. So, that is why this is called second derivative test, or I need to discuss with the concept called quadratic form and symmetric matrix and the classifications. That is how it connects. So, nature of Hessian matrix implies the nature of the critical point. That means, if I have a critical point, if I somehow guess some nature, and depending on that nature, I will say that at that critical point, my function attains local maxima or local minima, or it will be a saddle point. Okay, that I will talk about that. Okay, I have already discussed in that theorem. So, what is that? It's a very important theorem. So, because if I give some problem to talk about, check whether relative maxima or relative minima exist or not. So, this theorem very much useful to talk about that. What is that? if I have a function f from set E subset of R into R, okay, so it is a scalar field, and very important, the point x naught is an interior point. Okay, so this is very important statement. So I am starting with a scalar field and I am taking a point x naught which is an interior point. That means, of course, it is a point in the set E, along with there exists a neighborhood around the point x naught which is fully contained in that set, right. It is not a boundary point, it is an interior point. Okay. Suppose that all the second order partial derivative exist and continuous at x naught. Now, once I am assuming that all the second order partial derivative exist and continuous, okay, that means you can guess the corresponding Hessian matrix is symmetric matrix, because all the mixed partial derivative exist and they are equal the value, along with the fact that x naught is a critical point of f. Okay. So, what are the things? So, I am starting with a scalar field, I am starting with an interior point x naught, assuming that all the second order partial derivative of f at that point x naught exist and continuous, along with the fact that x naught is a critical point. Critical point means, if you remember, definition of critical point says that if all the first order partial, I am talking about second order partial derivative exists and continuous, that means it is expected first order partial derivative exist. Okay. So, that means if all the first order partial derivative exists, that has to be 0, right. So, this is the condition of critical points. So, critical points means a point is a critical point if all the, so two things are there. If all the first order partial derivative exist at that point, it has to be 0, then it is a critical point, and if one of the partial derivative does not exist. But this phenomenon will not occur here, because I am assuming that my function is second order partial derivative of my function exists at the point x naught, and therefore, in particular first order partial derivative automatically exists at that point x naught. So, therefore, not existence of one of the partial derivatives will not occur in this scenario. So, therefore, since second order partial derivative exists at the point x naught and continuous, so therefore, the corresponding Hessian matrix is symmetric matrix. On top of that, if I assume that x naught is a critical point means that first order partial derivative should vanishes at the point x naught, then look at the conditions I have given. What I am saying, let H be the Hessian matrix. I can talk about my Hessian matrix because I am talking about my second order partial derivative exists at the point. So, Hessian matrix makes sense. So, if my Hessian matrix is positive, of course, first you ensure that your Hessian matrix is a symmetric matrix, because second order partial derivative exists and they are continuous. So, therefore, it is a symmetric matrix. So, now I can talk about the kind of notion of positive definiteness of my symmetric matrix. Now, if H is positive semi-definite, of course, I already talked, if I have a symmetric matrix, how I can say that in terms of eigenvalues, what is the meaning of positive definite, that you know, if of all the eigenvalues are positive, strictly positive, then I am saying it is a positive definite. So, that means if your Hessian matrix is positive definite, then F has a local minimum at the critical point x naught. If your matrix H, which is a Hessian matrix, if it is negative definite, then F has a local maximum at that critical point x naught. If H is indefinite, then F has a saddle point at x naught, and if H is semi-definite, then it is inconclusive. That means the test is inconclusive. That means I cannot say anything. So, this is very nice theorem. So, using that theorem, so you can guess, okay, if I have a critical points, now these many critical points are there. Now, if you check whether those critical points, whether my functions have a local maxima or local minima. So, that is very important, or this point is a saddle point, or I cannot conclude anything. So, this is the theorem, it plays a very crucial role. So, that means if I have a functions from a scalar field, if I having a scalar field, if I am starting with the interior point which is a critical point first of all, and if all the second order partial derivative exist and continuous at that point, then of course, I can talk about my Hessian matrix. It is a symmetric matrix. Depending on the classifications of my symmetric matrix, I can talk about whether my functions attains local maximum at that point x naught, or whether it attains a local minima, whether my point is a saddle point, or whether I cannot conclude anything. So, that is how the full connections with the Hessian matrix and the quadratic forms. And of course, I can talk about the nature, or I can talk about the exist, or when my functions attain local extremum at that points, or whether the point is a saddle point, or whether I can say that I cannot conclude anything. So, this is called second derivative. So, that is what I have written. Okay. Okay. So, as I said, so in particular, if I take n is equal to 2, that means if I start with a functions from f E subset of R2 to R, that means you have 2 cross 2 matrix and you know all the entries, then you can easily say more explicitly for the existence of saddle point or like local minima or local maxima. So, what I am saying is that it is a corollary in the case, because I am putting n is equal to 2. Okay, what it says, let f be a functions from R2 to R. Okay. Let x naught be an interior point. Okay. Suppose that all the second order partial derivative exist and continuous, and x naught is a critical point. So, many things I have assumed. So, it is a functions from R2 to R, x naught is a critical point, all the second order partial derivative at the point x naught exist and continuous. Now, you go back to the Hessian matrix. You can form Hessian matrix because second order partial derivative exist. Since it is continuous, it is a symmetric matrix. Now, it is a 2 cross 2 matrix because I am starting with the functions from R2 to R, because Hessian matrix is nothing but the Jacobian of the gradient matrix. Gradient is a map from R2 to R2. So, therefore, the corresponding Jacobian matrix is of order 2 cross 2, and hence your Hessian matrix is a 2 cross 2 matrix. And what are the elements? You can easily calculate. So, first 1 element should be del 2 f del x square at the point x naught. 1 2 elements should be del 2 f del x del y. Now, it does not matter whether I am doing y first or x first, because value will be same. So, del 2 f del x del y is same as, so I should say del 2 f del x del y at x naught, which is same as del 2 f del y del x. That is because my second order partial derivative exists and continuous, that is why. So, irrespective does not matter. So, whether I am doing y first, x second, x first, y second does not matter, all are equal. And this is 2 cross 1 element, and 2 2 element means del 2 f del y square, del 2 f del y square, and this is del 2 f del x square. So, now I have explicit formula or form for Hessian matrix. Now, if I have a 2 cross 2 matrix, then in terms of determinant and the 1 1 element, you can talk about positive definite, negative definite, indefinite and semi definite, and you can conclude about the existence of local maxima, local minima, saddle point at the point x naught, critical point x naught. So, again look, if H is positive definite, that means a 2 cross 2 matrix, determinant should be strictly positive at that point x naught, along with the 1 1 element, that means del 2 f del x square at the point x naught should be positive. Then f has a local minima at the point x naught. If H is negative definite, that means determinant, of course, it should be positive at the point x naught, and the corresponding 1 1 element, that means del 2 f del x square at the point x naught is negative, then f has a local maxima. H is indefinite means corresponding determinant at the point x naught is strictly negative, then f has a saddle point at the point x naught. And if H is semi definite, that means if the determinant is exactly equal to 0 at the point x naught, then the test is inconclusive. So, that is very nice. So, therefore, if I have a functions from R2 to R, and if I have a point x naught, which is an interior point and which is a critical point, and suppose your functions has a second order partial derivative exists at that point and continuous, then you just form the Hessian matrix whose entries you know. What are the entries? Fxx at the point x naught, fxy at the point x naught, fyx at the point x naught, and fyy at the point x naught. Once I have that 2 cross 2 symmetric matrix, you just calculate the determinant and consider the 1 1 element. Depending on the sign of 1 1 element and the determinant, you can talk about the positive definite, negative definite, indefinite and semi definite, and then you can conclude your function attains local maxima, local minima, or it is saddle point, or I cannot conclude anything. Okay, that's how one can if I give a problem, that's how one can start with that. Okay, I'll talk about few examples, then you will see how that I can conclude that given that functions, if I ask you find the existence of local maxima or local minima or local extremum at some point, then how to proceed it. Okay. Okay, so that's exactly I have written. So, method to find an extremum values of f in an open set. So, this is very important, open set. So, that means if I have a function f defined from some open set S to R, okay, then what are the method I should go? I should go that, okay, if I go in this way, then I can talk about the existence of say local maxima, local minima, or it is saddle point, whatever it is. Okay. So, but I am giving the method to find an extremum value, could be maximum, could be minimum, in an open set. So, that means I am talking about a point in a set S. Now, S is an open set, that means each point should be an interior point, that means I am talking about the existence of extremum values of f in an interior point. So, therefore, automatically I am not considering the boundary points. Okay. And if suppose my function is very nice, that means suppose a first order partial derivative, second order partial derivative exist and continuous. So, that means you have to just go through the critical point, and in the critical point you calculate your Hessian matrix, classify your Hessian matrix like definite, positive definite, negative definite, indefinite or semi definite, and then conclude whether it will have a local maxima, local minima, saddle point. So, that is the process. So, I have written step 1, finding the critical points. So, what you have to do, first find the gradient vector of f at any point x, okay, that you have to do. Then you have to solution, suppose grad of f at x 0 that lie in S, they are the critical points. So, that means you have to first find the critical points. Now, if you remember what is the definition of critical point, that means a point is called a critical point if all the first order partial derivative exist and 0, all vanishes, or if one of the partial derivative does not exist, but that situation will not be here if I assume that all the first order partial derivative exist. So, therefore, if suppose my function is nice, so that means all the first order partial derivative exist, that means you just first calculate the gradient vector at the point x, then perform that equations, that del f del x1 at x 0, del f del x2 at x is 0 up to del f del x n many equations. You just solve it, you will have the collections of critical points. Once I have the collection of critical points, you have to just step to determining the nature of each critical point. Again, I am assuming that suppose second order partial derivative exists and they are continuous, therefore, you have the Hessian matrix which is symmetric, and then you just classify it. So, first one, step 2 is that for each critical point x naught, compute the Hessian matrix. Suppose you can do that, suppose all the assumption, whatever the assumptions needed, I am saying that yes, it is there. So, therefore, you will have the Hessian matrix. Now, determine whether H is positive definite or negative definite or indefinite or semi-definite, or by finding the eigenvalues of H in terms of eigenvalues of H, I also said. Okay. In case of 2 cross 2 matrix in terms of determinant and 1 1 element. So, there are plenty of things I have to. So, I have classified my symmetric matrix like definiteness and non-definiteness in terms of the quadratic form, in terms of the eigenvalues, in particular if I have a 2 cross 2 matrix in terms of the determinants and the 1 1 element. So, with that you just classify what is your Hessian matrix for in what category, and depending on the nature of H, make conclusions on the nature of the critical point. That means it is either local maxima, local minima, saddle point, or test is inconclusive. So, that is the method. So, if I give a problem to talk about, okay, find the extremum values of these functions, what you have to do? First, you have to find the critical points, and at the critical point, you have to calculate your Hessian matrix, and once you have the Hessian matrix, you find the nature of the Hessian matrix, and depending on the nature, you just conclude what will happen or what will be the conclusions for that matrix at that critical point. Let me see some example, then it will be more clear. Yes. So, first example, look. So, I am saying that let f be a function, it is a function from whole R2 to R. So, it is an R2 is an open set. So, therefore, I have a function, look the functions, function is very nice functions, it is a polynomial in x and y. So, therefore, all the first order, second order, third order, all the first order partial derivative exists, first order, second order, third order, so on and so forth. It is a very nice functions, in fact, it is a differentiable functions. Okay. So, if I have these functions, so what I am asking that okay, determine at which the points have a relative extremum or means relative maximum, relative minimum, what are the points you have to find out, and what are the points it is the function f has a saddle points. So, now since my function is very nice, so therefore, you have to just go through searching for the critical points and how to find the critical points. So, critical point means if all the first order partial derivative exist, they are 0, that is give you the one critical point, give the critical point, and another part is that if one of the partial derivative does not exist, but that situation will not occur here because my function is very nice. That means all the first order partial derivative, second order partial derivative, all of them are exist at any point. So, my function is perfectly all right. So, therefore, you have to just calculate your first order partial derivative at a point x y, and how many first order partial derivative will be there? Only 2, because it is a function from R2 to R. That means I can talk about del f del x and del f del y, perform del f del x, perform del f del y. You will have a function of x y, make it equal to 0, you will have equations, get the solutions, and these solutions will give you the critical points. So, step 1, finding critical points. So, you have to calculate f(x), partial derivative of f with respect to x variable. You can easily calculate, 1000 times you have done it, right. Keep the second variable y is fixed, think about it is a function of one variable and is function of x, perform the derivative. So, this is del f del x at x y, this is del f del y at the point x y. So, that means I have the first order partial derivative. Now, critical point means I have to find the solutions of f x y is equal to 0 and f y at the point x y is 0. That means del f del x at the point x y is equal to 0 is equal to del f del y. So, that means this is the this will give you the critical points, 0 is equal to del f del y. At the critical points, I have to look for the existence of extremum points, right. So, and my function is nice. So, now if this equation del f del x at the point x y 0 and del f del y at the point 0. So, I have written, so this is equal to 0 implies 2x minus 2y is equal to 0. F y of x y is 0 means this is equal to 0. If you solve it, I am not going to solve it here, very two simple equations. If you solve it, you will end up with the x y should be either 3 3 or minus 1 minus 1. Okay. So, that means I have two equations, I have solutions 3 3 minus 1 minus 1. Two equations means what? I have only two partial derivatives because I am having a function from R2 to R. Okay. So, that means if you perform del f del x, perform del f del y, del f del x is equal to 0 will give you one equation, del f del y is equal to 0 will give you one equation. You solve that equation, get the solution, these are the critical points. And then you have to calculate the Hessian matrix and see the nature of this Hessian matrix. So, therefore, I have concluded thus the point 3 3 minus 1 1 are the critical points of F. Now, your step 2, determine the nature of each critical point. Nature of each critical point means what? You have to first calculate the what will be the Hessian matrix at that critical point and look at the nature of this Hessian matrix. Now, since it is a functions from R2 to R, then what will be the Hessian matrix? So, what is the order of the Hessian matrix? It is a 2 cross 2 matrix, because F is a function from R to R, then what is the gradient vector del F? So, the F is a map from R2 to R, okay. Then your gradient of F is a map from R2 to R2, and therefore, the corresponding Jacobian matrix at the says any point, in particular critical point, it should be a 2 cross 2 matrix that I already explained. So, this 2 cross 2 matrix what? This is the matrix, right? This is the matrix fxx, fxy, fxy, fyy, right. So, you have to calculate the second order partial derivatives, all second order partial derivatives evaluated at the point x naught, and you have a 2 cross 2 matrix, and you just identify the nature. And once I have a 2 cross 2 matrix, then you can identify the nature, you know, in terms of determinant and the 1 cross 1 1 element. So, at the point 3 3, so one can check, you can easily check, because partial derivative fx fy is there, you have to perform one more partial derivative, that means you have to take the derivative of fx with respect to x and y, and you have to take the derivative of fy with respect to x and y. It will give you all mixed partial derivatives. You have to form the Hessian matrix, then the corresponding determinant, if you calculate, it will be positive. If you check at the point 3 3, 1 1 element, which is nothing but del 2 f del x square at the point 3 3, it will give you 2 positive. So, therefore, nature of this Hessian matrix is actually positive definite, and therefore, f has a relative minimum value at that critical point 3 3, very simple. And what about at the point minus 1 1? It is a critical point, I already checked. Again, you just perform the Hessian matrix. If you calculate, the corresponding determinant is negative at that point minus 1 and 1 1 element. Okay, since determinant is negative, so it is a saddle point. That's it. That's what I have asked. So, therefore, what I have done, my function is very nice. It is actually polynomial. All the first order partial derivative and second order partial derivative, they exist, they are continuous. So, step 1, you calculate first order partial derivative. Make first order partial derivative fx fy is equal to 0, it will give you equations, get the solutions. Once I have the solutions, these are the critical points. So, I should check only on those critical points, that is it. Okay. Step 2 is that once I have the collection of critical points, you just have to calculate the Hessian matrix, all those critical points, and see the nature of the Hessian matrix, and then conclude whether my function has a saddle point or has a relative maxima or relative minima. So, this is example 1. Another example I have given, again this is a function, again this time it is a function from R3 to R, it is a function from R3 to R, okay. Again it is a polynomial in x, y, z, so all the first order partial derivative, second order partial derivative, they exist, they are continuous. So, first you have to calculate all the critical points and find its nature. So, critical point means what? Apart from the del f del x, del f del y, del f del z equate to 0, it will give you 3 equations, you get the solutions. So, if you get it, you will see 2x is 0, yes, x is 0, y is 0, z. So, only 0 0 0 is a critical point. So, that means you have only one point, you have to check the Hessian matrix and its nature. So, at 0 0 0 point, the corresponding Hessian matrix, if you calculate, of course, it is symmetric because second order partial derivative exists and continuous, and look at what are the eigenvalues. It is a diagonal matrix, right. So, it is minus 2, minus 4, minus 6. So, that means it is actually all the eigenvalues are negative. That means it is a negative definite, and therefore, it is a 0 0 point is a local maximum point of f. Very nice. Okay. So, that is very kind of straightforward. Okay. So, it depends. Okay. If you have a more number of critical points, I mean it is expected the calculation will be more, because at each critical point you have to see the nature of the corresponding Hessian matrix. Okay. So, one more example I have given. So, find the maxima, minima and saddle points of this function. Again, this is a very nice function. It is a function from R2 to R. It is a combination of polynomial and exponential functions. Again, first order partial derivative, second order partial derivative at any point exists, they are continuous. So therefore, your Hessian matrix is symmetric. So first you have to find the critical points, and then you have to see the nature of the Hessian matrix, all those critical points. So critical points how to find? Perform del f del x and del f del y equate to 0, del f del x is equal to 0, del f del y is equal to 0. Those equations will give you some solutions. So f x is equal to 0, f y is equal to 0. If I have this equation, that equations, and if you solve it, these are the possible solutions. So how many solutions? 2, 2, 4 plus 1, 5 critical points are there. And you have to check the corresponding Hessian nature of the Hessian matrix at those points. If you check it, so at the point 0, 0, so this is the value f x x at the point 0, 0 is 2, 0 minus 2, and hence the determinant is negative. So therefore it is a saddle point. At the point root 2, 0, this is the corresponding value of the f x x, f x y, f y y, and determinant if you calculate, this is 16 by e square, that means it is positive. Okay, and f x x element, this is this negative, that means it will have a local maxima. At the point this one, determinant is positive, 1 element is negative, that means local maxima. At the point 0 root 2, again determinant is positive, but 1 element is positive, that means local minima. Similarly, at the point this one, determinant is positive and 1 element is positive, so that means local minima. So this is, I just complete the example. So you just have to give the solution. Already it is written f x f y, you just kind of justify yourself, yes, these are the 5 critical points we will have, and corresponding Hessian matrix, if you calculate, these are the things will come. That you should complete it in details in home. Okay, so other terminology I should say, so a critical point, sometimes in some books it is called a stationary point. Okay, a critical point is called a stationary point. And okay, that fact you know, that if I have a function f, so to talk about at which points my functions attain its maxima minima, before that I have to somehow ensure that yes, maxima minima exist. So that means this is the one, if I have a function f from E subset of Rn to R, if A is closed and bounded, that means if it is compact, then it attains maximum and minimum value. Then what are the points? That will have the kind of method. That means you have to find critical points, you have to find Hessian matrix, you have to find the nature, and then only you will conclude that yes, at that point it attains maximum, local maxima, at that point it is local minima and saddle points. Okay, so I think I should stop here. Okay, so this is the kind of method I have explained. That means how to, given a function f, how to find what are the points my function attains local maxima, local minima, or what are the points, saddle points. In my next lecture, I will talk about the existence of global maxima and global minima, because till now I have a nice functions, and I am kind of starting with a open set. So therefore, I am just only considering a interior point or only critical point because my function is nice. Now suppose you have a function f, it's defined not on a open set, suppose it's a square. If suppose I am starting with a compact set or closed sets, it will have a say boundary point. So then if I want to talk about the existence of global extremum, that means global maxima, global minima. So of course I have to look through the interior point. That means in the interior, what are the critical points I have to look, along with I have to look for the boundary as well to find that what are the points my functions having a global extremum. Okay, so only interior point will not work. I'll have to look through in the boundary as well to talk about global extrema and global minima. Okay, I think I should talk about in my next lecture, along with of course Lagrange multipliers method and total exact differentials. Okay, for the timing I think stop here. Thank you.